Hi everyone, my name is Chaitanya. I am pursuing BTech second year first semester from EC branch. Today onwards I explain a topic about random processes and mathematical models for unpredictable phenomena. A comprehensive exploration of stochastic models, theory and its applications. What are the random processes? A random process, also known as a stochastic process, is a mathematical construct that model phenomena evolving unpredictably over time or space. Finally, it is defined as a collection of random variables indexed and two by a parameters, typically time denoted as xt. Visual representations. Each random variable xt represents the state of the system at a time t. Its key characteristics: unpredictable evolution systems that change in way impossible to forecast with a criterion, and random variables. Each point in the time represent as a random outcomes, temporarily dynamic evolution over time or space parameters. Core components of its random processes, and every random process consists of three fundamental elements that define its structure and behavior: index set, state set and sample paths. Index set represent time, can be discrete or continuous. State space, set of all possible values each random variables xt can take in. These discrete values 1, 2, 3, or 4. Now, sample paths. A single outcome or tragedy of the random process. Each path show one possible evolutions. Classification of random processes: discrete time, discrete state, and discrete time and continuous state, continuous time and discrete state, continuous time, continuous states. Okay, now discrete time and discrete states. These parameters take discrete values and state space in finite or countable sets. Discrete time and continuous state. Time parameters take discrete values by, but state space is continuous. Continuous time and discrete state. This time parameters takes continuous values but state space is discrete. Continuous time, continuous state. Both time parameters and both state space continuously values. Markov process and the memoryless properties. A Markov process is characterized by the Markov property. The future state depends solely on the current state, not on the sequel of events that led to it. Visualization the memoryless properties. Key characteristics: a discrete time. Transition between state occurs at a discrete time steps. Transition matrix and probability defined by the matrix P, where Pj is a probability of transition from state it to state J. Memoryless. Only the present state matter or not how to get here. Markov chain example: weather modeling. A sample weather modeling with the two states sunny and rainy. The weather tomorrow depends only on today weather, not on the weather history. Two state weather models, sunny or rainy. Okay. Next, transition probability: sunny today, 90% chance to sunny tomorrow, 10% chance rainy tomorrow, rainy today, 20% chance sunny tomorrow, 80% chance rainy tomorrow. Now, Poisson process and counting random events. A Poisson process is a continuous time counting process that models the number of events occurring randomly and independently over a given time interval at a constant average rate lambda. Key properties. Now, independent increments. Event in disjoint the time interval or dependent. Independent. Stationary increment. Distribution depends on interval length, and interval times time between the events are exponential with mean 1 by lambda. Memoryless properties. Similar to the Markov process has the memoryless properties. visualization representation. Poisson process properties and applications. Key properties. Independent increments. Event is disjoint the interval or independent. Stationary increments. Distribute depends only the interval length or not starting point. Exponential inverse times and the time between event follows the exponential distribution with mean 1 by lambda. Memoryless properties. Similarly to Marcus proper, future events do not depend on past. Applications. Call center modeling. Call arriving at a average rate. Traffic flows. Vehicle arrives at increment. Queuing theory. Queuing theory. Queue theory. Random arrives in the queue systems. Poisson process visualization. Poisson process step function representation. C1s. Now, Brownian motion, random particle movements. Brownian motion, also known as Wiener process, is a continuous time stochastic process that models the random movements of particles suspended in a fluid. It is a fundamental concept in stochastic calculus and serves as a building blocks for more complex models. Sample path sequence. Key features has a model process, continuous sample path. Paths are the continuous but now we are differable and independent increments. Future movements is the independent past movements. Gaussian increment flow on a normal distribution. Fractional nature and self similar structures of a cell. Now properties of Brownian motion. A standard Brownian motion is WT is a continuous time stochastic process with these definition properties. Now zero start, continuity, independent increment, Gaussian increments. Zero start, W0 equal to 0 with probability 1. Continuity, sample path or continuity function of time, independent increment. Wt plus s equal to Wt is independent of Wu for u less than or equal to t. Gaussian increment Wt plus s minus Wt equal minus n of 0 comma s. Now the differentiable being continuous Brownian motion path are almost now difficult to meaning that instant velocity is undefined. Fractional nature exhibit the self similarities and the fractional dimensions. Introduction to stochastic calculus. Stochastic calculus is the branch of mathematical that extend the concept of differentiation and integration to stochastic process, and particularly those with irregular non-differentiable path like Brownian motions. Now, key characteristics of it and consistent theory, providing a framework for the integration stochastic process with respect to each other stochastic process. For irregular path, essential for the process with the path that are almost now very differentiable. Foundation for the now the stochastic differential equations. SD are the differential equations with the stochastic process typically involving this wide nose of Brownian motion used in the model systems with random proportion. General formula dx of dxt equal to mu of xt comma t into dt plus psi of xt comma t. Xt equal to stochastic process and mu of xt comma t drift terms. Sigma of xt comma t is diffusion terms. D omega t Wiener process increments. Now, Itzo-Lemma, the stochastic chain rules. Itzo-Lemma is a fundamental result in stochastic calculus that serve as a chain rule for the function of its process. Now, key processes. Additional correlation team and occurs the differentiation of the variation of stochastic process and velocation effect and capture how the velocity affects the function evolutions. Now its formulas. For a twice difference function f of t comma xt, where xt is an into process, df of t comma xt equal to dou f by dou t plus mu t dou f by plus 1 by 2 into sigma t square and dou f by dou t square into dt plus dou t by dwt. The terms 1 by 2 sigma square del of f by del of t square by dt in the its correlation terms and its applications. Stochastic optimization deriving the SDs from the transform variables. Finance derivation and correlation is blank and stochastic models from the optimizing pricings. Engineering applications. Random process providing the essential frameworks for the modeling and analyzing the system with the inherent uncertainty across engineering disciplines. Signal processes, communication systems, and control theory. Now, communication system control theory. Now, signals processes, filtering noise from the signals from the clear data and interpretation, and modeling image behavior in the convolution algorithms, enabling the efficient data reduction without significant information loss, and analyzing error probabilities in the communication channels, and designing modulation scheme for the optimized data transmission, optimizing network performance in the noise environments, control theory, developing the stochastic controls and systems for the uncertain inputs, and optimizing system performing under random fluctuation, and financial applications. Random process provide the powerful frameworks from modeling finance and markets and pricing, dividing and managing the risk in the presence of uncertainty. Optimizing pricing. The black shows as machine models uses geometric and Brownian motions. Enables the theoretical pricing of the European style optimize. Account for the essence by the price evaluation and the random movements. Risky managements. Value at risk calculation, credit risk modeling, conflicts potential from marketing fluctuation, and enable to mitigation solution for the financial uncertainty. Asset modeling. Now, stochastic valuation models and interesting rate process modeling for the casting movement, marketing movements, and understanding complex financial essential dynamics. Physical science applications. Random process provide a powerful framework for the understanding the phenomena across the physics, statistical mechanics, and fluid dynamic quantum mechanics. Brownian motion describe the particle movements in fluids, insight to different diffusion and transport the phenomenon. Model for the turbulent and the irregular fluid motions, understand the complex and fluid behavior. Now, quantum mechanics, stochastic interpretation of quantum phenomena, describe of the quantum noise and probabilistic behaviors. Key way and future directions. Key ways and mathematical framework. Random process provide a robotic and frame for the understanding the phenomena with inherent uncertainty. And fundamental types. Markov chain, Poisson process, and Brownian motion from the essential model from diverse systems. Analytic tools. Stochastic calculus provides a powerful methods for the complex systems subject to random fluctuation. Future directions. Interdisciplinary application, expanding the application across emergent file and complex real world systems, and computational methods, advancing numerical techniques for the solving complex stochastic systems. Now, theoretical advancements and continuous evolution for the stochastic calculation and random process theory. Thank you, everyone.